Hi and Assalamualaikum. My name is Siti Khairulnisya binti RASHED under supervision of Dr. FARRAHSHAIDA binti Muhammad SALLEH. The panel that will evaluate my study is Dr. NORLIANA binti Muhammad ABBAS and I am Dr. YUSOFF. Today, I will present my final year project to study the simulation of PLA materials using Solidworks for injection molding process. Presentation outline consists of introduction, literature review, problem statement, objectives, scope of project, methodology, result and discussion, conclusion and recommendations, and references. First is introduction. PLA. Polylactide or polylactic acid is a biodegradable aliphatic polyester that has been widely researched in various fields ranging from food packaging to automotive interior products for its range of applications. The raw material of PLA, lactic acid, can be extracted from renewable sources of the fermentation of corn, beet sugar, and cane sugar. As seen in the figure 1, the life cycle of polylactide polymers started from the raw material, which is biomass and corn, then to the conversion of dextrose to lactic acid. Next, the purification by distillation to condensation process. Then the product is produced for packaging, textile, and medicine use. The use of PLA will benefit to the reduction of annually renewable resources and reduce global greenhouse effects. Injection molding and simulation. Injection molding is a technique for obtaining molded products by injecting heat molten plastic materials into a mold, then cooling and solidifying them. This approach is ideal for the mass production of goods with complex shapes and play a major role in the plastic processing industry. Injection molding shortens the curing time, removes the requirement to prepare the rubber prior to molding, and minimizes mold handling and scrap when compared to compression molding. The use of simulation software is necessitated by the need to make the correct assumptions about the simulation model and to be familiar with the process parameters used to process a specific plastic material. Literature review. Polylactide material. First is the study of industrial use by Stefano Fiori on 2016. His findings that PLA has received so many attention from the industry sectors because of the low price and its commercial availability. In fact, PLA is a high-strength, high-modulus polymer with appropriate barrier properties and easy convection machinery processing. Next is the study on physical and mechanical properties of PLA and their functions in widespread application, a comprehensive review by S. Farrah et al. On 2016. Lactic acid-based polymers have a wide range of mechanical characteristics, including soft and elastic as well as rigid and high strength. When the preferred mechanical characteristics are needed, semi-crystalline PLA is preferable to the amorphous polymer. Semi-crystalline of PLA has a tensile modulus of 3 gigapascal, a tensile strength of 50 to 70 megapascal, a flexural modulus of 5 gigapascal, and a flexural strength of around 100 megapascal. Upon breaking, the sample elongates to about 4% of its original length. Injection molding process. The study on optimization of mold temperature profile and process parameters for red line reduction and short cycle time in rapid heat cycle molding by Satoshi Kitayama, Ryoto Ishizuki, Masahiro Takano, Yoshikazu Kubo, and Shuji Aiba on 2019. The summary of the study is red line reduction is a critical aspect of plastic injection molding as it results in high quality surface look and high strength of plastic product. To accomplish both red line reduction and high productivity in fast heat cycle molding, it is critical to modify both the mold temperature profile and other process parameters. Although the trial and error approach is commonly used to modify them, it is a long process. Next is the study on optimization of injection molding process parameters in the molding of high-density polyethylene HDPE by Dixon David Olado et al. On 2018. Shrinkage is one of the main factors which cause dimension changes to the component. Optimal process parameters may be reduced by configuring the injection molding machine. It was observed that cooling times were more successful in reducing shrinkage and refilling pressure. The lowest efficient factor for reducing shrinkage was the injection pressure. Next, the simulation process. The study on effect of mold opening on the properties of the PLA samples obtained by foam injection molding by Valentina Walker et al. On 2018. This study findings was the 3D model part was imported to the simulation software to simulate the injection molding process for thermoplastic. For PLA materials, the greater viscosity causes the pressures within the injection chamber and therefore a greater compression of the shot, which result in better foam injection molding. Lastly, the study on development of mold rheology test sample via CADE-MOD 3D simulation by Atman M. et al. On 2018. The simulation in injection molding process could indicate the processing parameters involved, such as the temperature of the melt, filling time, packaging pressure, and the remaining cooling time, as well as the behavior of shrinkage and warpage. In order to produce high-quality samples for the mold development for rheology test, the development will include the design, simulation, and analysis and fabrication process need to be considered. The cavity system, runner system, and gating system as the main factor in the analysis also is crucial for the mold development. Problem statement. The use of other conventional thermoplastic as a plastic packaging materials that will take a longer time, up to 1,000 years to decompose, can harm the environment compared to the PLA that will slowly degrade in a slightly damp climate over several months to a year that will degrade into carbon dioxide, methane, and water. Next, numerous manufacturers of injection molded plastic products would like to discover via trial and error by developing a new product. A well-designed mold is necessary to produce a high-quality product with an attractive look and good mechanical characteristics. However, these trials and errors typically add to the ultimate cost and take time. This will result in a long-term loss of competitiveness. Third, lack of study or research on the simulation process on injection molding for PLA material has been done before this. Fourth, shrinkage and warpage of the PLA materials could occur with the increasing of coolant and mold temperature. The important parameters in the injection molding process such as forming the final cavity shape, cooling elements, and gouting points will affect the simulated product. Objective. First, to simulate the injection molding process for PLA materials for producing a packaging part in Solidworks software. Second, to develop mold design for runner, gating, and screw in injection molding process for PLA materials. Third, to analyze the shrinkage and warpage to the injection molding parameters. Next is the scope of project. First, the development of the 3D part model and mold by using Solidworks software. Next, the identification of important parameters such as injection pressure, injection temperature, and mold temperature of the injection molding process for the PLA materials is also crucial before the simulation process. Next, the simulation of the PLA materials' flow ability in injection molding process will also be done by using Solidworks software. Lastly, the output of the flow behavior from PLA material simulation can be used as a reference for the injection molding process parameters. Methodology. The dot bond was developed by using Solidworks software. The dimension of the dot bond model that developed has a length of 60 mm, 50 mm width, and 4.5 mm thickness. Next, the essential data include physical properties, mechanical properties, and rheological properties of the PLA were imported to the plastic database in user-defined database in the Solidworks plastic, since the properties of PLA did not exist in the default database. Then, the mold system that consists of runner, screw, and gating system were designed in the Solidworks plastic. It is important to have a good mold design because one factor contributing to the final quality of injected parts in injection molding was mold design besides process condition and the material characteristics. Next is the meshing process, where the flow domains are divided into smaller pieces representing an element to analyze the fluid flows. The size of meshing used was 2.5 mm with a boundary layer of 2. The solid tetrahedrohybrid meshing type was used because in a Solidworks plastic, a solid mesh is more preferable. In contrast, solid tetrahedrohybrid gives the best result for the cavity inserts and the runner. The SolidWorks plastic simulation is used to analyze the plastic filling process, parameters and plastic injection molding, which influence the quality of the product created using the plastic injection molding method. In this injection molding simulation process, the injection parameters such as injection temperature, injection pressure, and mold temperature were selected before starting the process. Flow plus X plus work analysis was selected to simulate the injection molding process due to obtaining the material's flow behavior such as filling time, seam marks, volumetric shrinkage, and wet line. Lastly, the final result was analyzed and identified from the simulated part that focused on the filling time of the cavity, shrinkage, warpage, seam marks, and wet lines. This result is crucial for studying the flow behavior of the plastic materials and for the future research studies. Result and discussion. The processing properties of the injection molding parameters as table 1 is important in simulation of injection molding process of the PLA material. First is the flow result, filling time. The result indicates that the molten plastic has successfully filled the dot bond model with a maximum filling time of 2.8571 seconds and a minimum of 0.00178 seconds. Process factors such as injection pressure, filling, packing pressure, melt temperature, mold temperature, and coolant temperature may affect the plastic filling behavior that will lead to the product quality issues. Proper injection pressure will influence cavity filling, whether it is filling or not, and prevent shrinkage, void, seam, and short issue. Furthermore, the location of the gates play an important role for the molten plastic to fill the cavity parts, characteristics, and final appearance of the product. The volumetric shrinkage at end of fill. Maximum volumetric shrinkage occurs at the yellowish to orangish color of the dot bond part with a value of 13.6146 volume percent since it was the thickest part in the dot bond part model. Meanwhile, the minimum volumetric shrinkage occurs at the blue color region near the gate screw and runner area with a value of 1.1248 volume percent. Height shrinkage rates will occur in thick sections of plastic parts that do not undergo a sufficient packing stage during the molding process. The shrinkage rate for the PLA materials typically was in the range of 0.3% to 0.5%. However, when evaluated at the processing temperature and the ambient temperature, shrinkage of molded plastic components can be as high as 20% by volume. This indicates that the volumetric shrinkage obtained was still in the range. In addition, the high volumetric shrinkage readings can cause a seam mark or void inside the part model along with an uneven volumetric shrinkage which may contribute to warpage. The melt temperature and mold temperature are two process variables that considerably affect the part volumetric shrinkage response. Next is the seam marks. Maximum seam marks occur at 0.03696 mm for both end areas of the yellowish and orangish color of the dot bond part model, which the part has the largest surface area. Meanwhile, the minimum seam marks occur at 0.0015 mm at the blue region of the runner, screw, and gate that has the lowest area. Commonly, the seam marks appear at the thickest area of the part. Optimize the process parameters settings such as melt temperature, injection time, injection temperature, fill, type switchover, type time, injection rate, and coolant temperature can reduce the seam marks. However, seam marks also can be influenced by the material selection for the mold. Next is the wet line. As can be seen, there was no wet line visible on the dot bond part model, but only visible at the bottom edge of the runner and gate because wet lines are unavoidable in parts with groove holes. The maximum value of the wet line occurred at 131.01 degree, while the minimum value was only 0.1 degree. The wet lines also can occur if too low of melt and mold temperatures. The gate system also contributes to external and internal defects like red lines, matte, and seam marks. The occurrence of red lines in part also can result in the injected components become weakening or breaking. Next is the pack result. First, pressure at end of packing. The maximum pressure at end of packing was at the entrance of the injection location, which the surface area was the smallest that generates the high pressure with a value of 17 megapascal, while the minimum value was 0.1 megapascal at the blue region part. The packing pressure was when the revolving screw regulates the pressure applied on the activity during the packing step. With a thinner cross-section, the flow resistance is larger and high pressure are necessary to pack the components. Defects such as seam marks, hesitation, and potential leak into the cavities might appear on the parts that were packed too lightly. Next, density at end of packing. The maximum density occurs at the runner, screw, and gate area with a small surface area with a value of 1.252 gram per centimeter cubic. In comparison, the minimum density was 1.0917 gram per centimeter cubic that occur at the light blue region that has the largest surface area. The density at end of the pack result can assess how well a part has been packed. Usually, the density result should be consistent across the part, but as seen in the figure, the density does not uniform throughout the part. That was why the shrinkage does not uniform throughout the part too. The volumetric shrinkage at end of packing. The maximum volumetric shrinkage occurs at the orangish to the yellowish region of the dot-bond part model with a value of 11.6106 volume percent and the minimum value of 0.0093% at the blue region. The shrinkage will occur rapidly in regions of the plastic part that not receive an adequate pack stage. If the volumetric shrinkage at end of the packing plot has substantial red regions, difficulties could occur. As can be seen, there is no red region on the part, which indicates that the shrinkage at the low condition which only minimum seam marks and warpage will occur. Next, residual stress at post-film end. The maximum residual stress was 65.57 megapascal, while the minimum value was 0.24 megapascal. Residual stress are present in the viscoelastic polymer material because of the non-uniform cooling and pressure fluctuation during molding. Residual stress in a component will almost always cause a fracture or part will experience some other physical change after molding. Lastly, the warp result. The maximum total displacement for the warpage is 0.7 mm and the minimum value was 0.007 mm. The animation shows the intended shape of the molded part was distorted in small displacement only. Additionally, the molecular structure of the substrate amorphous or crystalline has a role in minimizing warpage. Moreover, warpage is generated by non-uniformity of shrinkage as a result of residual strains created by the complicated temperature fluctuations within the mold. Antiseptic warpage is critical when working with components whose area exceeds their thicknesses. Conclusions. Study has successfully simulated the injection molding process of the PLA materials by using Solidworks. The important injection molding parameters such as melt temperature, mold temperature, packing pressure, and injection pressure will substantially affect the quality of the final product. Defects in the injection molding process such as red lines, seam marks, shrinkage, and warpage were common issues. They can be avoided if the proper process parameters of the injection molding were applied. Injection molding simulation software such as Solidworks Plastic, injection molding problems may be identified and fixed prior to the start of the production. The result of the simulation of injection molding process of the PLA materials can be as a references for the future study. Recommendation. Future production of PLA materials, it is possible to mix the PLA with other materials to create a good biodegradable plastic option. The optimization of injection molding process parameters such as melt temperature, mold temperature, packing pressure, and injection pressure can produce the better quality of the final product. In future, a cooling stage can be introduced to improve the simulation analysis. By introducing cooling stage, the cooling efficiency of plastic molded parts may be increased. Besides that, various gate locations and multi-cavity molder also can be introduced to achieve a variety of simulation results for better processing conditions. See the references. This is the references that has been used in this study. That's all from me for my final year project study. Thank you.